MN is our diameter. Here's the center of our circle, and point A is up here, where A is the midpoint of the semicircle and B is close to M. We're going to pick a point C on the other side of the diameter, and we'll call these intersecting points P and Q. So we're asked to maximize D, which is the distance from P to Q. So first, we're going to find an expression for the distance from M to P. Let's draw a simplified version of this circle with just BC. Drawing in MB and BN, we have a 90-degree angle here at B, and we're given that this length is 3/5 and the diameter has length 1. So we know that the distance from B to N is 4/5. Now we're going to use same base, same height to compare the distance from M to P to N. This ratio is the same as the ratio of the areas of triangles BMP here on the left and the area of triangle BNP on the right. I'm going to draw these segments underneath the diameter. Again, from same base, same height, the ratio of the triangles underneath, MCP and CPN, have the same ratio. Here we're going to note that if we have two equivalent fractions, they're going to be equal to the sum of the numerators and the sum of the denominators. So I'm going to add these two areas. So in our numerator, we have BMP plus MCP. That's this triangle on the right, the area of triangle BMC. And these two triangles in the denominator, they sum to the area of triangle BNC on the right. Now I'm going to use this area formula on these triangles. For triangle BMC, this is 1/2 BMC times the sine of angle BMC, and then the same thing for the area of triangle BNC. Note that BNCM is a cyclic quadrilateral, so these opposite angles, BMC and BNC, sum to 180 degrees. So from our unit circle, we know that the sines of these two angles are going to be the same. We find these two angles in the numerator and denominator of our fraction here, and we'll cancel them out along with the 1/2. And this is the ratio we started off with in the beginning. Let's take a look at this ratio, BM over BN. We have those dimensions already. That's 3/5 over 4/5, or 3/4. So MP over PN is 3/4 of MC over NC. We'll stop here and go to the second part, which is to find an expression for the distance from N to Q. And we'll redraw a simplified diagram of our circle. Recall that A is the midpoint of this arc. This is C, and this intersecting point is Q. We'll do a similar thing as before. We'll find the ratio MQ to QN. Let me fill in these segments. This is the same as the ratio of the two triangles in the top half and the two triangles in the bottom half. This is equal to the sum of the numerators and denominators. The numerator is the area of the triangle on the left-hand side, AMC, and the denominator is the area of the triangle on the right-hand side, ANC. And we'll use our sine formula for the area of a triangle. We have another cyclic quad here, so these angles AMC and ANC sum to 180 degrees, so they're going to have the same sign. So we can cancel out these factors, leaving AM, MC, AN, and NC. Since A is the midpoint of this arc, these two distances AM and AN are the same, so they cancel out. And we're left with MQ over QN is MC over NC. Let's bring back this equation that we got from part 1. First, let's let T be MC over NC. So MQ over QN is T, and MP over PN is 3/4 of T. Let's bring back that circle and recall that our diameter MN is 1. We can get rid of some of these variables by noting that PN is 1 minus MP and MQ is 1 minus QN. So MP over PN, we'll replace that with MP over 1 minus MP, and this is equal to 3/4 T. And our other fraction, MQ over QN, we'll replace this with 1 minus QN over QN, and this is equal to T. In both of these equations, we can solve for MP. When you do that, you get MP is equal to 3T over 3T plus 4, and then solving the second one for QN in terms of T, this is 1 over T plus 1. For this problem, we're trying to maximize D, which was the distance from P to Q. This is the diameter minus MP and QN. That leaves behind PQ. Our diameter is 1, and we'll substitute our expressions for MP and QN. Now we'll multiply by the denominators and combine like terms and write it as a a quadratic in t. So we'll end up with 3dt squared. The coefficient of t is 7d minus 1, and our constant is 4 times d, and this is equal to 0. Recall that t is the ratio of these distances, so it's a positive real number. If this is true, then the discriminant of the quadratic above is non-negative. So let's substitute for b squared minus 4ac. We'll expand this out and combine like terms, and you should end up with d squared minus 14d plus 1 is greater than or equal to 0. So this is a quadratic inequality in d. So let's find the roots of this quadratic. Using the quadratic formula, we get our two roots, 7 plus 4 root 3 and 7 minus 4 root 3. Since this is an upward opening parabola, we're greater than or equal to 0 when d is greater than or equal to 7 plus 4 root 3 or less than or equal to 7 minus 4 root 3. We note that 7 plus 4 root 3 is greater than 1, which is the diameter of our circle. So this is not a valid answer for d. Checking our other solution, 7 minus 4 root 3 is approximately replacing root 3 with 1.7. This comes out to about 0.2, less than 1 and not negative. So our maximum d is 7 minus 4 root 3. When written like this, the sum of r, s, and t is 14. If you'd like me to solve any other math contest problems, please leave them in the comments.